In this video, we'll talk about support vector machines, what the mathematics are behind these things, how they work, and when you might use them as a classifier. So support vector machines often fall into what's called the black box of machine learning techniques. In particular, it's not really well deserved with support vector machines. The ideas underlying these are actually very simple. So, support vector machines are actually a pretty new technique. Decision trees were first introduced in the 1990s, so were these, or SVMs. There's sort of a logical progression here. So the first thing that we'll do is actually talk about the first type, or the first introduced type of support vector machines, the maximal margin classifier. After that, we'll talk about the support vector classifier, what that represents, and then finally, support vector machines. So we'll build up to creating one of these. And these are intended for binary classification only, so you can't do regression with these. These can work when there are two or more classes. The way we handle that is using one versus everything else classification. So what's the probability of being in one particular category versus not being in that category? Support vector machines are built using hyperplanes. Let's define what those mean first. In p-dimensional space, a hyperplane is just a flat subspace of dimension p minus 1. So it's just anything with one less dimension. So in two-dimensional space, the hyperplane is a flat line. In three-dimensional space, the hyperplane is a plane. In the real world, the hyperplane would be like a sheet of paper. Now in p dimensions, some equation, beta 0 plus beta 1x1 plus beta 2x2 plus all the way to beta p x p equals 0 defines the p-dimensional hyperplane. If there is a point that satisfies that equation, then x lies on the plane. Now, let's say that x is either above the hyperplane, is greater than 0, or below the hyperplane, less than 0. Well, then we've got this p-dimensional space. It's divided into two disjoint pieces. And the left-hand side of these inequalities is certainly reminiscent of something like a regression model, perhaps. So that's the idea that we'll use to build these. So as an example, the hyperplane that you're seeing here is a really simple one. So we have a two-dimensional function. We've got 1 plus 2x plus 3y as this dark line here. So in two-dimensional space, this is our line, our hyperplane. We'll classify into two classes, below and above. Now, let's say that we have a data matrix, n times p dimensions, that consists of n training data points in p-dimensional space. We're going to further make an assumption that observations fall into two classes. We're going to categorize or code these a little bit different. So we'll have a -1 class and a +1 class. That's so we can construct the hyperplane. So the hyperplane is some function in terms of beta 0, beta 1, beta 2, all the way to beta p. We'll put the cut point for the hyperplane at 0, so we need to define our classes as being beyond that 0 range. We're going to try to find what's called a separating hyperplane. So if we can, we'd like to find a hyperplane that splits the training data into these two classes as efficiently as possible, meaning there's going to be no misclassification. We're going to have a straight split. So take a look at an example. This is actually the iris data set recoded so that the Setosa irises are over here in blue. The Virginica and Versicolor irises are in this very dark blue, almost black. Where would we put this hyperplane? Well, somewhere around here might be a good candidate. We could draw a line there, although we do have an observation on the wrong side of the hyperplane. We could draw a line here. We still have this one observation on the wrong side of the hyperplane. Which line is better? Is there a different line that's optimal? We'll find out. What we would like to do, if we can, is generate what's called a separating hyperplane. So this separating hyperplane is essentially a perfect classifier. For all y equal 1, so everything in that one category, we always will end up with a regression equation or a prediction above the hyperplane. For everything in the -1 category, we'll always end up with a prediction below the hyperplane. If this exists, then how do we handle the test observations? Well, we plug them in. We classify them to class 1 if they are above the hyperplane, classify them to class 2 or class -1 if they're below the hyperplane. If this is existent, it's probably not unique. So we still have a question of which one is optimal. The optimal hyperplane that we'll use is something called the maximal margin hyperplane. The idea is that this maximal margin hyperplane is farthest from the training observations. So it's the one that is farthest from the training data. We'll do this by finding the minimum perpendicular distance from each observation to the separating hyperplane. That's called the margin. And then we'll choose the hyperplane where this margin is largest. So essentially, we'll maximize this margin subject to a constraint. The particular constraint here is that the sum of all of these regression coefficients, beta squared, must be equal to 1. What this constraint is going to do for us is guarantee that observations will be on the correct side, the second constraint here guarantees that all observations will be on the correct side of the hyperplane. So if we're on the above side, then this y will be positive. If we're on the below side, this y is a -1. That will make all of this now negative. If this first constraint is met here, the sum of the squared coefficients, then it turns out that this second constraint is actually the perpendicular distance. So with these two, we can find these perpendicular distances. We'll choose m, or choose these betas to maximize m. Okay, awesome. But what if we've got a data set like this one, where a separating hyperplane maybe doesn't exist? Well, we've got some choices. We might be able to find a separating hyperplane in smaller dimensions, but then we've lost data from our problem. So instead, we might use what's called a soft margin to attack this. The soft margin introduces some wiggle room, or what we'll call slack, into this equation. So the soft margin maximizes with m times 1 minus some error term. This error term is going to be a slack variable. So this allows the margin to decrease in some cases, so introduces some wiggle. Will require that these epsilons are greater than 0, and further will minimize the total number of these epsilons. So we don't want to introduce too much slack, so we'll use some tuning parameter c to indicate how much slack we're comfortable introducing into our model. So then the solution to these constraints becomes the support vector classifier. So it's not the same as that marginal classifier. It's not a support vector machine either. We're not quite there yet. The support vector classifier doesn't perfectly separate the two classes, so we're allowing for error here. This does provide some greater robustness to the individual observations, so we're not tuning that line to be perfect. This also helps us avoid overfitting to the training data. However, since we do have a constraint on the sum of the squared beta terms, we should always pre-process our data before we apply this technique. Support vector classification is another one of those models like k-nearest neighbors and regularization that does heavily depend on pre-processing. Okay, So we'll take the iris data set and we'll build a classifier to predict whether or not a flower is a setosa iris. For visualization purposes here, we'll use only 2 inputs. And further, we haven't classified or we haven't standardized this data yet. However, with just 2 inputs, the effect of this probably isn't too terrible. So the way this code works, we will first define these irises as setosa. So if they are, we'll assign 1. If they're not, we'll assign a -1. We'll then remove that original species indicator just so we're not predicting species membership based on species. So we'll create our data partition for our training data. Here we'll build the pre-process step directly into train because this is a pretty simple pre-processing. We don't need to write a standalone recipe for doing something like this. For visualization purposes, I've chosen to use just 2 inputs, sepal length and sepal width. So we'll take a look at this tuning parameter, C. So we're holding that C, or that sum of the slack terms, at a value of 1. Overall, our accuracy is really good for this model, 0.99. When we look at the training data, it's almost perfectly separable. What that means is there's only one observation in the training data where we're missing. The one observation is right here, and it's that one that was kind of tricky to wiggle around anyway. But we can see we've got a pretty good classification otherwise. 2, -1, +1, so not too bad. If we include all possible inputs with this data set, we end up with a perfectly separable model. Now, unfortunately, we can't really visualize this 4-dimensional model, but looking at the accuracy, we have an accuracy of 1. We've perfectly classified these iris flowers. Now, let's say that we're in a situation where we don't have a clear linear separation between the points. So this is an example from the ML Bench library that I like to pull out sometimes. This is a data set, or a function, that generates data in a spiral pattern. So we have -1 and +1 rotating around each other. Probably not going to get a good linear classifier here. We can certainly try it. So we fit this. Our accuracy is 0.476. Remember, we're predicting into one of 2 classes. So this model is actually doing worse than chance. Not great. Here's what our classifier looks like. So maybe not the best technique for a data set such as this. Now, we can expand this slightly by introducing nonlinear decision boundaries, so perhaps fitting a higher order polynomial function. So a degree 2 model would look like this. We will now have different terms or different betas for each power. We'll still add some constraints here, so we'll constrain these squared betas now for all of the powers, so these betas may end up being fairly small if this is a high dimensional problem. We will also introduce slack into this with the epsilon. To extend this to even higher degree polynomials, expand the range of k. So here we have k being just a squared term. There's no reason we couldn't use a cubed, quadratic, and so on. But there is a downside. Eventually, this model is just going to get too complex for us to work with. So the solution is to extend this linear support vector classifier using a different technique, using kernels. So this kernel-based technique, we've kind of alluded to these in the past. Essentially, we're going to take the inner product of 2 vectors to help us build this model. So the inner product is defined below. For 2 vectors, xi and xk, the inner product is the sum of each of the element y's values. So the first entry from xi times the first entry from xj plus the first entry or second entry from xi times xj, and so on. The linear support vector classifier then looks like this. We build a model with an intercept term and then taking some alpha term times the sum of the inner products. Each of these inner products is taken with respect to a new data point, a data point that we would want to predict for, say, x without a subscript. It turns out, or you can show that this alpha is non-zero only for support vectors in the solution. So only for support vectors where this is non-zero. So to extend this or make this even more general of a process, what we'll do is take the inner product and replace it with the kernel function. So kernel functions are, again, just measures of the similarity between two observations. So we'll use those to build our model. We've got a lot of different choices that we can take. We could, of course, use the linear kernel. We could use the polynomial kernel. We could use the Gaussian kernel or the exponential kernel. There are a lot more that are implemented in R as well. So this support vector machine then just takes the support vector classifier and uses a kernel function. So what ends up happening is that we're allowing for more flexible and non-linear boundaries, which is pretty nice. So let's use this support vector machine to maybe do a prediction. So can we use this to predict, say, whether a person has diabetes? So here I'm taking a data set that we've seen before from the ML Bench library, the Pima Indians diabetes data set. The first thing that I'm doing here is dropping the NAs. Then what we'll do is create a training data set, testing data set, and we'll build the model. So SVM linear as a method uses that linear support vector machine. We get our final model. We get some measure of our training error. Overall accuracy is 78%, so not too bad. What happens if we try, say, a different kernel? So maybe I'll try a radial sigma kernel. So I'll just change my method. It looks like our training error has gone down slightly. Our accuracy has gone up slightly. So maybe this radial kernel is a little better. We could also look at, say, a polynomial kernel, which I will leave to you to try and see how this works. But we have tons of different options. I'll briefly go to the caret documentation just to show you how many options there are. So if we go to the support vector models in caret, looking at the guide, chapter 7, these are all possible implementations or slight tweaks on building support vector machines. So there are loads of different kernel functions that you can implement to build these. That's one of the reasons why these support vector models are often referred to as a black box. Changing this kernel function slightly changes the mathematics to a point where most maybe casual machine learners aren't as familiar with the mathematics of what's happening underneath. The other reason or the other tool or the other property that turns these into sort of a black box or a difficult to understand approach is the n-dimensional or p-dimensional nature of this problem. This Pima Indians database, for example, has several input variables. I believe there's something like 10 different input variables. In order to really truly visualize and understand what this model is doing, we would need to visualize a 10-dimensional space to truly see the hyperplane. So that's one major downside of support vector machines as an approach. Like I mentioned, support vector machines can handle more than 2 classes, but there's a couple different approaches that we can try. So you can try 1 versus 1 classification with these support vector machines. Essentially, you'll build choose 2 support vector machines, each comparing a pair of classes. Or you'll do 1 versus all classification. So you'll build k support vector machines, each comparing just a single class. So even though support vector machines can work with more than 2 classes, it's not really recommended unless you're willing to build lots and lots of models. So I'll leave some support vector machine problems for you to play around with in the homework, and I will speak to you soon.